The accessibility of wearable eye tracking devices has opened up the possibility for research of gaze data, both in academic fields and for commercial uses. When the tracking becomes wearable, it is possible to research gaze data in the wild studies. But as the opportunities for these studies rise, so does the complexity of the gathered data. When considering video data recorded by a participant in a natural setting, the data can quickly become very complex. We utilized the pupil invisible wearable eye tracker glasses to create a study at Produktion, an art museum in Aalborg, with ordinary museum guests to obtain gaze data pertaining to specific paintings. The collected data needs to be interpreted and analyzed manually as it is now. This is a tedious and time-consuming task for researchers. Based on this, we present the development of a system that allows for automatic annotation of paintings, seen through a wearable eye tracking device without having to collect a big data set. Our goal is to develop a tool which takes the video data generated by an eye tracking device and automatically annotate and cut out the important parts of the video and remove the rest. To do this, we utilize the oriented fast and rotated brief algorithm, also called ORB, which finds key point matches between two images no matter the scale, in our case, a reference image of one of the chosen paintings and a video frame. In this paper, we present two approaches to solve the problem, a fully automatic and one where we manually input timestamps for when participants look at a painting. The pipeline for the manual approach is as follows. Take recorded data. Manually annotate event start and stop in Pupil's cloud platform. Download and extract important data. Run the video and gaze data cutter function to only get timestamps that fall inside of manually annotated events. Get individual videos from each painting. And finally, run the best image match function to get which paintings are present in which videos. The pipeline for the fully automatic approach requires no manual annotation of events, and instead utilizes the ORB function on the full eye tracking video to annotate timestamps for when a painting is being looked at. To test our implementation, we asked visitors at Produktion to record their gaze data using the provided pupil invisible eye trackers. 23 visitors agreed to participate, consisting of 15 females and 8 males. The participants had to walk around and look at paintings in a small section of the museum, which consisted of 12 paintings. The average time spent walking around the exhibition was 7 minutes and 10 seconds. A comparison between the results of manual and automatic recognition of paintings was performed, and found that overall, the automatic event creation fell short of a satisfactory performance. The majority of the paintings achieved F1 scores above 0.6, which indicates that 60% of the time, these paintings were found at the accurate timestamps. Multiple paintings were, however, found more often than they were actually present in the video, which resulted in false positives. This seems to be because of multiple paintings, sometimes being fully in frame at the same time, or paintings being visible while the participants were moving from one painting to the next. 4 paintings in particular were in close proximity and were found at the same time periods in multiple tested videos. Additionally, a comparison between the automatic recognition timestamps and the ground truths were performed, with the ground truths consisting of the timestamps we annotated for the manual pipeline. The automatic event notation time exhibited an average deviation of 12.19 seconds, with a notable outlier in the case of the painting Sabotage, which deviated by 180.61 seconds. Upon excluding this outlier, the notation time showed an average deviation of 2.82 seconds. In the paper, we have presented a way to automate the manual labor of annotating events by incorporating the computer vision algorithm ORB. Additionally, we have automated the removal of irrelevant data from the video content and the sorting of collected video data. Furthermore, we have implemented a functionality that superimposes the gaze data created by the eye trackers onto the reference image to visualize gaze patterns of participants. The aim was to demonstrate the use of the algorithm in a real-world scenario, like a museum, and the reliability and robustness of such a system. We argue that with a few further improvements and fine-tuning, the algorithm could produce a satisfactory result.